All right, welcome back to the deep dive. Today we're diving into a paper with a pretty technical title, SDD4DGS, Static Dynamic Aware Decoupling and Gaussian Splatting for 4D Scene Reconstruction.
Sounds a bit intimidating, right?
Yeah, maybe a little, but don't worry, we'll break it down. Essentially, this paper tackles a really cool challenge. How do you build a realistic 3D model of a scene that changes over time? Like imagine a street with cars moving or people walking around, and you're trying to recreate that entire scene in 3D just from a bunch of 2D videos.
Exactly. And this kind of 4D scene reconstruction, as it's called, is becoming super important in a ton of areas. Like think about VR and AR, those immersive experiences, or even things like self-driving cars that need to understand how the world around them is changing.
Right, makes sense. And the problem is, existing methods for doing this often treat all parts of the scene the same way. Whether it's a building that's standing still or a car zipping by, they're kind of lumped together in the calculations.
Yeah, and that can lead to some problems. This paper points out that static parts of the scene, like buildings or trees, often occupy a huge portion of the visual data, like 75 to 85%. But the dynamic elements, the stuff that's actually moving, make up a much smaller percentage.
So it's like the background is grounding out the interesting stuff.
Kinda. The paper uses this phrase, low energy anchors. Basically, these static regions can kind of pull the optimization process towards them, making it harder to accurately capture the details of the moving objects. Imagine, like, trying to film a hummingbird in flight against a busy background. It's hard to keep the focus on the bird when everything else is competing for attention.
Oh, I get it. And it's not just that the dynamic stuff gets lost, right?
Yeah.
The dynamic objects also mess things up for the static parts of the reconstruction. Think about shadows, for instance. A person walking past a building casts a moving shadow, which makes it harder to get a clean, consistent reconstruction of the building itself.
Exactly. So there are problems coming from both directions. And that's where this paper's solution, called SDD4DGS, comes in. The core idea is to decouple the static and dynamic parts of the scene so they can be handled separately. And they do this within the framework of Gaussian Splatting, which has become a popular way to create high-quality 3D models, especially for real-time applications.
So how does this decoupling actually work? What's the secret sauce?
The secret sauce is what they call a dynamic perception coefficient, denoted by the letter F. Basically, it's a probability assigned to each of the little 3D Gaussian blobs that make up the scene. And this probability tells you how likely that particular Gaussian is to belong to a dynamic object.
So each little piece of the scene has its own score for how much it's probably moving around.
Right. And this F isn't just a fixed value. It follows a Bernoulli distribution. Think of it like a coin flip. It can be heads dynamic or tails static with a certain probability for each outcome.
Okay, I'm following. So as the system learns, it figures out these probabilities for every single Gaussian blob.
Exactly. And they use these probabilities in a really clever way when they render the scene, like when they project those 3D Gaussians onto a 2D image. The rendering process now depends not just on time, as in traditional 4D Gaussian splatting, but also on this dynamic perception coefficient F for each Gaussian.
So it's like each little blob is saying, hey, I might be moving, so take that into account when you're drawing me.
Pretty much. And then, to make things even more interesting, they actually deform these Gaussians over time to account for movement. And they do this by blending together two sets of parameters. One for the static state of the Gaussian and one for the dynamic state. And guess what? That probability F comes into play again, acting as a weight to determine how much of each state to blend.
Oh, that's pretty neat. So they have a recipe for both a still version and a moving version of each blob. And that probability F is like the chef deciding how much of each recipe to use.
I like that analogy. Now, to make sure those probabilities actually settle into clear static or dynamic values, they use a binary entropy loss. It's a technique that basically encourages the system to be decisive, to push each Gaussian towards either 0, definitely static, or 1, definitely dynamic.
So no fence sitters allowed.
Exactly. But here's the thing. If you force this binarization too early in the training process, it can actually make the model perform worse overall.
Makes sense. Like if you're learning to play the piano, you wouldn't start by trying to play a super complex piece perfectly. You'd start with the basics and gradually work your way up.
Exactly. So they use this clever technique called a progressive constraint schedule. Basically, they gradually increase the influence of that binary loss over time so the model can first get a good grasp of the scene's overall geometry before being forced to make those hard decisions about static versus dynamic.
So it's like easing into it. Okay, I like that. What else did they do to make this work well?
Well, they have another trick up their sleeve. Automatic supervision. The idea here is that areas of the scene that are hard to reconstruct perfectly, like areas with a lot of motion blur, are probably dynamic.
Makes sense. You're trying to take a picture of a speeding car. It's going to be more blurry and harder to capture than a parked car.
Exactly. So they use pre-trained features from a model called DynOV2 to estimate the reconstruction uncertainty in different parts of the scene. And they use this uncertainty to create motion masks that highlight the areas that are likely moving.
Oh, that's cool. So they're basically using the model's own confidence levels to guide the training process.
You got it. It's a form of self-supervision, which means they don't need any manual labeling to tell the model which parts are moving. And this whole process is incorporated into their overall loss function, along with the original Gaussian Splatting loss and that progressively weighted binary loss we talked about earlier.
So they put together a pretty sophisticated system here. But how well does it actually perform?
The results are pretty impressive. They tested SDD4DGS on 5 different benchmark datasets covering a range of scenarios, including some really challenging real-world driving data from the Kitti dataset. And in every case, they outperformed existing state-of-the-art methods.
Really? That's significant.
And they didn't just improve the dynamic parts of the scene, the static reconstructions were also better. So by decoupling these two elements, they actually managed to improve both simultaneously.
That's really cool. And what about those ablation studies you mentioned earlier? What did they learn from those?
So the ablation studies basically involved removing different parts of the system one at a time to see how much each part contributed to the overall performance. And what they found was that every piece mattered. The dynamic perception coefficient, the progressive constraint, the automatic supervision, they all played a crucial role. And they even have some cool visualizations showing how their method achieves a better separation of static and dynamic elements compared to previous approaches.
It seems like they really nailed it with this approach. So where does this fit into the broader landscape of 4D scene reconstruction?
Well, if you think about the history of this field, we've come a long way from traditional 3D reconstruction techniques to neural rendering approaches like Gaussian splatting. And while there have been attempts to incorporate temporal information into Gaussian splatting, those earlier methods usually treated the whole scene uniformly. This paper really highlights the importance of explicitly considering the differences between static and dynamic elements.
And how does this work compared to other attempts at static dynamic decoupling?
So there have been approaches using things like manually defined masks or self-supervised methods within neural radiance fields, or NeurAFs. But what's unique about this paper is that they're doing this decoupling within a Gaussian splatting-based dynamic reconstruction framework, and they're doing it in a completely self-supervised manner. It's a pretty significant contribution to the field.
I'm starting to see why this is such a big deal. So just to recap the key takeaways here. The core innovation is that probabilistic dynamic perception coefficient, which allows for a more nuanced way to assign those Gaussian blobs to either the static or dynamic camp. The progressive constraint is really important for training the model effectively, and the automatic supervision using uncertainty is a clever way to provide guidance without needing any manual labels. And the results, both quantitatively and visually, show that this approach leads to a clear improvement in 4D scene reconstruction.
Exactly. And when you think about the potential applications, it's pretty exciting. This could lead to more realistic VR and AR experiences, better special effects in movies, and even safer autonomous vehicles. Basically, any field that relies on understanding how 3D scenes evolve over time could benefit from this kind of advancement.
Absolutely. Now, speaking of future directions, let's get to our novel notions segment. What are some ideas for extending this research even further?
All right, let's speculate a bit. So the current approach uses a binary distinction, static or dynamic. But what if we could make that dynamic perception coefficient more continuous? Like instead of just a 0 or 1, imagine a whole spectrum of dynamicity.
Interesting. So a tree swaying in the wind might have a medium dynamicity score, while a speeding car has a very high score. And a building, of course, would be close to 0. It could allow for a much more nuanced representation of movement.
Right. But it would also introduce some challenges. How do you define and learn those intermediate levels of dynamicity? You might need to explore different types of probability distributions or come up with entirely new ways to represent motion. But the potential payoff is huge. Imagine being able to render complex natural scenes or even subtle facial expressions with a level of realism that's just not possible with current methods.
That's a really cool idea. And for our second novel notion, right now, the system relies primarily on motion cues and reconstruction uncertainty to distinguish static and dynamic elements. But what if we could incorporate semantic understanding into the mix?
I like where you're going with this. We know that certain objects, like cars, are more likely to be dynamic than others, like buildings. Even if a car is temporarily stopped, its semantic identity gives us a clue.
Right. So how do we integrate that knowledge into the system? Maybe we could use pre-trained models that can recognize different types of objects and use that information to bias the initial dynamic perception probabilities.
Yeah. Or maybe even use the semantic information to guide the deformation network itself. If the system knows that a certain set of Gaussian blobs represents a person, it could predict more realistic human-like movements. It's like combining the power of geometric understanding with semantic understanding.
Exactly. Imagine a scenario where a person is standing still behind a translucent curtain. The system might struggle to detect their motion based on visual cues alone, but if it knows that those blobs represent a person, it can maintain a higher probability of them being dynamic, even when they're not visibly moving.
That's a great example. By incorporating semantic information, we could create much more robust and consistent 4D reconstructions.
So, building upon the foundation laid by this paper, there are some really exciting avenues for future research. And the core concept of static dynamic awareness seems crucial for truly capturing the complexity of our dynamic world.
Definitely. By explicitly addressing the differences between these two fundamental elements, we're opening up a whole new realm of possibilities for 4D scene understanding.
All right, so to wrap up our deep dive, this paper introduced SDD4DGS, a really clever framework that brings static dynamic awareness to 4D Gaussian splatting. It uses a probabilistic dynamic perception coefficient, a progressive constraint schedule, and automatic supervision to achieve some really impressive results. And beyond the technical achievements, this work has the potential to significantly impact a wide range of fields, from VR and AR to autonomous driving and beyond.
And as we continue to develop technologies that blur the lines between the physical and digital worlds, it's going to become increasingly important to accurately model these dynamic environments. And I think this research is a big step in that direction.
Absolutely. For those who want to dig into the nitty-gritty details, we've got a link to the paper in the show notes. And as you think about the future of 4D scene understanding, consider this. How will our ability to create truly realistic and dynamic digital twins of our world impact our interactions with it? Will it fundamentally change how we design, experience, and even perceive reality itself?
That's a great question to ponder. And on that note, thanks for joining us for this deep dive. We'll see you next time with another fascinating piece of machine learning research.